people on Zoom ready?
We are good.
Okay.
Is the room ready?
Perfect. All right. Our next speaker is Mellah, and they'll be talking about particle acceleration around spinning black holes. Take it ahead.
Thanks, Vicky, and thank you for being here. That's so good to see you all live again. Today, I present recent results on the topology of the magnetic field around Kerr black holes, around spinning black holes, and I will discuss this topology, the consequences of this topology in terms of particle acceleration at reconnection sites. But first of all, let's look at a few observational motivations for the different ingredients of our models. Accreting black holes seem to be surrounded by hot corona, where photons are upscattered by relativistic electrons up to high energy. Florian Kangemi, who has a talk tomorrow, identified this high energy component in Cygnus 61. It's present in the low Earth state, but also in the high soft state, which supports the idea of tenuous plasma around the black hole. A similar situation is expected in around supermassive black holes like Sagittarius A star, where we observe non-thermal flares on a daily basis. These flares are due to synchrotron emission, which suggests that magnetic field matters. In agreement with polarization measure with polarimetric studies in Cygnus 61, but also more recently in M87 star. The Event Horizon Telescope collaboration showed that the plasma is embedded in a strong poloidal magnetic field, which is brought and sustained by the accreted material. So in this talk, and last but not least, of course, these black holes have jets, which are thought to be rotation driven. In Cygnus 61, some diagnostics indicate that we might be dealing with a maximally spinning black hole. Things are even less clear in M87 and Sagittarius A star, but thanks to the joint effort of the Gravity and EHT collaborations, we should have more information in the years to come. In this talk, I want to present simulation results of the dynamics of the plasma and of the electromagnetic fields in the corona. And I want to stress on the key role played by the magnetic field lines seated in the accretion disk, but which close within the event horizon of the black hole. So our numerical setup is the following: a black hole spinning around this axis with the event horizon and the magnetosphere. Thanks to the Kerr shield coordinates, we can go from 30 gravitational radii all the way down an internal boundary inside the event horizon. So they are global simulations. We assume axisymmetry around the spin axis and a plus minus z symmetry, and the resolution of our simulation is high enough to capture the kinetic scale of electron-positron pairs that we inject, such as the force-free regime can be achieved. In the initial state, this plasma is permeated with poloidal magnetic fields, which threads the event horizon and is anchored at its foot point in a steady, aligned, and perfectly conducting disk in prograde Keplerian rotation around the black hole, and which stops at the innermost stable circular orbits. So this type of coupling configuration of the magnetic field has been studied by Dimitri Uzdensky and more recently Yajie Yuan and collaborators, but they worked in the force-free approximation. So they were not able to capture dissipation or changes in the topology of the magnetic field. However, they derived a very important property, which is actually illustrated on the relaxation of our initial state that you can see here. If the black hole spins, the magnetic field lines are going to be sheared because in the ergosphere, they are dragged by the lens steering effect, and they rotate at an angular speed which is different from the one of their foot points on the disk. So you can see this. So then like a toroidal component of the magnetic field is going to develop, propagate outward, and will lead to the opening of the magnetic field lines beyond a certain distance. You can see this as the general relativistic analog of what happens to magnetic field lines around a neutron star. So beyond the neutron star, the light cylinder of the neutron star, the magnetic field lines open. The main difference here is that you need some material to bring the magnetic field and sustain the magnetic field, since the black hole cannot sustain its own one. So 4 different regions appear in these simulations: magnetic field lines threading the event horizon and extending to infinity, and they rotate at half of the black hole angular speed. Magnetic field lines, open magnetic field lines anchored in the disk and inclined enough to launch wind via the magnetocentrifugal Bluntford and Payne effects. Some in the innermost region, some coupling field lines, which will enable energy and angular momentum to be transferred between the black hole and the disk. And the current sheet right here, a highly non-force-free region where electromagnetic energy is dissipated. So here I just represented the poloidal magnetic field lines, but let's have a look at the full 3D structure of the magnetosphere that you can see right here. So you retrieve this open field lines anchored in the disk. You have here the separatrix, which is the outermost closed magnetic field lines, which delimits a zone on the disk between the separatrix and the ISCO, where you can have these exchanges of energy and angular momentum. And in the polar regions, you have these open field lines crossing the event horizon, which are twisted enough to funnel an electromagnetic jet a la Bluntford-Nyack. So we computed for different black hole spin the magnetic flux in the jet region that you can see in green on the left axis. And we also computed the Poynting flux that you can see in blue on the right axis. So in this jet region. And provided we use the correction term at high spin introduced by Tchaikovsky and collaborators 10 years ago, we retrieve something, a dependence which matches, a dependence on the black hole spin, which matches what you expect in the force-free approximation. So that's a good checkup. And so an important thing is that the actual value, the physical value of the power of the jet will depend not only on the black hole spin, but also on the scale of the magnetic field, the magnetic flux in the jet, which will depend on the magnetic flux which is carried by the accreted material. So now comes the crunchy part, the microphysics. Most of the magnetic dissipation occurs at this Y point, which was the outermost, the farthest point on the separatrix. This point, the position of this point depends on the spin of the black hole. Here you have for different spin of the black hole, the event horizon, which is the solid line, and the separatrix, which is the dashed line right here. And you see that for higher spin, the Y point where the dissipation will take place is much closer from the black hole, and it makes a huge difference because then you are probing a region where the magnetic field is much more intense. So if you want to evaluate the amplitude of this dissipation, you can look at the Lorentz factor of the particles. Because we really follow each of the particles in this particle in cell approach, we can really follow the electron and positrons one by one. So we can monitor, we can evaluate the fraction of the electromagnetic field, which is tapped by particle acceleration. And you see that for a maximally, for a high spin and for a low spin, you get a very different configuration with a very low acceleration efficiency of the particle acceleration for a spin of 0.5, but a very important spin particle acceleration for a higher spin. So the higher the spin, the higher the Lorentz factor of the accelerated particle, but they are also accelerated much closer from the black hole. So in a region where the magnetic field is much more intense. So in terms of emission, you will see in a moment that it means a lot. So this side of dissipation of energy could explain how you inject relativistic electron and positron in the corona. So that could be a source of heat for the corona, but that could also be an intense emission site for hard X-rays. So then that offers you another possibility for the Lampos geometry. So the idea would be that now we are no longer dealing with a point source on the spin axis of the black hole. But if you unfold this Y point in 3D, you have a geometry which looks like more something like this, with like one ring above and one ring below the plane. So that's here for like the three-dimensional representation. That's rocket science. Please don't do this at home. And then you will get like the black hole in between, with this ring just above the plane and another ring below the plane. So that could be another possible geometry for the lamppost itself. So I know that I have a lot of like timing experts in the audience. So I did my homework in terms of variability of the motion of this white point. That's what's represented here by this dots, by these maps. So the white point moves and will tend to get farther and farther as the separatrix is stretched. And when the plasmoid is emitted, the motion, the white point comes back much closer. So the characteristic time scales are given right here. They are a bit short to be detected in Cygnus X1, and they are too short to explain the flares in Sagittarius A star, but they could be an interesting source at some point. I will pass very quickly on the energy and angular momentum exchange within this coupling region, which could explain some hotspots in the inner region of the disk. And I will finish with now the synchrotron emission map. So here you get like a logarithmic maps of the synchrotron emission maps you would get for these particles in this magnetic field for maximally spinning black hole. You get different angles of view, and you recognize these reconnection rings I was illustrating with this glass a minute ago. So yeah, as a summary, the non-thermal aspects of these objects really require to go for like a particle in cell approach for kinetic descriptions of these objects with these hybrid magnetospheres, which develops in different regions. We also worked with retrograde disk, but the configuration is totally different and does not lead to particle acceleration. So the angle between the spin of the black hole and the rotation axis of the disk does matter. And we also worked with thick disk. So for supermassive black holes, we retrieve qualitatively the same results. So the perspective are like better synchrotron images, the light curves to have an idea of the variability, and the 3D extension to see how the Y points behave on this Y reconnection ring around the black hole. So the corona might actually be a double corona like this, if I want to base myself on the sketch of that Vicky posted on Slack. With this, I will thank you for your attention and take any question or comments.
Thank you, Ulyss. Any questions in the room? I don't, oh, yep, there's.
Just a quick comment. So the millisecond flares have been observed from Cygnus X1 there was a paper by Anjay quite some time ago. So you might be interested also to check that.
Okay, so I would really like to know more about it. So we should chat.
I don't see any hands up on Zoom. I hope I'm not missing anyone. Any questions in the room? If not, let's thank Ulyss again